Welcome to day 1 of the Intuitive Limits course. In this first day we're going to talk about the intuitive idea behind limits, and we're going to talk a little bit about notation also. So let's start with a very basic idea. Let's suppose we want to figure out the area of the circle. From basic geometry we know that the area of the circle is given by this magic formula. If you want to find the area, you use the formula pi times radius squared. But that is easy enough, but let's suppose for a minute that we don't know this magic formula. Let's suppose that we want to find this area and we don't know this formula. What other approach we can take to at least approximate this area? And Archimedes was thinking about this problem, and he came with a very interesting idea. He said, let's consider this polygon as an approximation to the circle. It is not a very good approximation, but it is a first approximation. And I'm going to draw the circle around the polygon like this. And here I paint in red the areas of the circle, the area of the circle that is not covered by the polygon. So we can think about these red areas as the error we are making with the approximation. So the idea here is that to approximate the area of the circle, we're going to take the area of this polygon, because it is quite easy to calculate the area of a polygon. For example, you can take it apart. You can take this rectangle here and these two triangles. You calculate the area of each of those shapes and you add them up and you get the area of the polygon. So that is the idea. We simplify the problem by solving an approximate problem that is much easier to solve. So this is a first approximation. How can we make a better approximation? We can make a better approximation by increasing the number of sides of the polygon. If we increase the number of sides, we get a figure like this one here. We can see that the red areas decrease in size. There are less red areas now. So we're making a smaller error now. So the idea here is that we're going to keep on increasing the number of sides of the polygon, and with that we're making better and better approximations to the area of the circle. So the question here is, can we continue with this process indefinitely? And the answer is yes. And when you do that, when you continue this process indefinitely, what you're doing is taking a limit. You're taking the limit. You're taking the limit as the number of sides approach infinity. And this simple idea, called the method of exhaustion, was used by Archimedes a long time ago. So you can see what is the idea behind limits with this very simple example. The idea is that, well, let's keep talking about functions now. Because in calculus what you're most interested about is functions. So we had to talk about limits of functions. And to begin with, we're going to consider a very simple function, f of x equals x squared. The graph of this function is this one. And here I took the point x equals 1 and the corresponding value of f of x, that is also 1. And the first thing when you look at the graph is that you can take any value on the x-axis and you can see what is the corresponding value of the function here. But here, when we're studying limits, we're not interested in that kind of information. We're interested in what the function, how the function behaves. And let's talk a little bit about that. Here, for example, when x approaches 1 here in the x-axis, f that takes values on the y-axis also approaches 1. And when this happens, what we use this very fancy notation, and this is read: the limit as x approaches 1 of f of x equals 1. So the idea here is that when you take values very near to the number 1, that is, x is approaching 1, f of x is approaching 1 here in the y-axis. And you may ask, why is this useful? I already know that f takes the value 1 at x equals 1. And that's a very interesting question. I made that question when I first learned calculus, and the answer is that many times you're not interested in what the function, in the value of the function at a specific point. You're more interested in what the function approaches at that point. To see that, we're going to consider a little variation of the previous example. Here we have a piecewise function. This function takes the value 0 at x equals 1 and the value x squared if x is not 1. So the graph of this function is the same graph we had before, but here we have a hole at x equals 1, because at x equals 1 f of x will be 0, and for all other values of x, the graph is the same. It's the same parabola here. So the question here is, what is the limit now when x approaches 1? Where's the limit of f of x? And the answer is that the limit is the same. It is 1 again. And in this case, the limit is not equal to the value of the function. Here the value of the function is 0, and it is not equal to the limit. And well, this means that it doesn't matter what is the value of f of 1. We could take, instead of f of 1 equals to 0, we could take 1 million, for example. And those are the types of limits that are most useful in calculus and all other sciences. So in the next videos, we're going to keep talking about how to deal with limits, and we may begin to solve some problems. So that's all for now. Thank you for watching, and see you next time.